Hi everyone and welcome to this new video. In this video I continue my Linux Privilege Escalation series, and specifically in this episode we will talk about Linux file system permissions. So the idea is to analyze all the things related to the permissions in the Linux file system. This means that we will understand how permissions are structured, how we can read and understand the permissions on a given file or directory, and now we can update the permissions on a given file or directory. And finally, we will talk about two specific systems which allows us to interact with permissions in special ways, and these are the SUID and GUID bits that can be set on an executable, and the sudo subsystem, which allows us to execute commands as other users. So that's the idea. I hope the video is enjoyable. If you have some feedback, please leave it in the comments, subscribe to the channel, and share this video with like-minded people, so we can go on and enjoy the video. So the first thing I want to mention is that in my first video of the Linux Privilege Escalation, I showcase a lot of different commands. So here we see the org file for that video and all the commands that I showed, for example, the basic commands like username, hostname, working directory, and so on and so forth. Then we showed some file system commands, then some resource management commands, for example, disk usage, processes, network interfaces, open ports, and so on and so forth. So a lot of different commands I showcase. Now, to understand how all of those commands worked, there is a system called the man pages, which essentially is a documentation that tells you exactly how those commands work, what kind of options they take, what kind of arguments they take, and stuff like that. So to access all this information, you have two ways essentially. Either you download the man command. So using your package manager, depending on your distribution, you can download this command, which is called man, and it is a shorthand for manual page. And when you have this man, you sort of like can access locally the documentation. So for example, if you do man ls, it's gonna give you the documentation for the ls command. And we can do it here in this other here. So I can do man ls here. I do man ls, I execute it, and here I have the documentation for the ls command. And notice that this kind of documentation has the same format, so let's redo it. So we have the name of the command, so the short name and a long description, list directory contents. Then we sort of have like a description on how we can use it. And so this is the synopsis. The idea is, okay, you use ls by giving a bunch of options and then a bunch of files. These three dots mean that you can have more options and more files. And the description tells you exactly what it does. List information about the files, the current directory by default, sort entries alphabetically if none, or, and here it tells you essentially how the various options modify the behavior. Now, reading these pages is not too trivial. You're gonna get used to it, to the specific syntax that information are displayed. But the important thing is that with enough practice, you will be able to understand how to read it, which means that if you then forget how to do a specific action using, for example, the ls command, then you can quickly search through the page to understand what was the specific flag. So for example, if you do the -a, it says, do not ignore entries starting with dot, which means that typically by default it ignores the entries that start with dot, and if you want to include them, if you don't want to ignore them, you have to do -a. And you know, by going forward, you see all the different options, so there's like a lot of stuff here. And this is for the ls command, of course. And then I think that at the end, like towards the end, you also see like the author, some other information. Sometimes there are even examples, not all the time, however. And so that's essentially the idea. So I wanted to talk about this because in the previous episode I showcased a lot of commands, and to access the documentation for all those commands, the man pages are extremely useful. So you can say, for example, man ps, and it says report a snapshot of the current processes, or you can do man df, and it says report file system space usage, and it's the same thing, it's the same idea. You just go read the main page, you see all the different flags, you do some trying, of course, because it's a lot of practice too. So that's the idea. If you don't want to download these main pages, you can just go online. Here there are online main pages, so here I put a link. So the idea is, how do you use these main pages? You can either search by individual sections. So like you have 8 pages and each page is filled with different commands. So like different pages have different like commands. And sometimes you have the same name for the command but present in different pages, because maybe the page 1 contains certain information and the page 3 contains other information. So you might find essentially the same name in different pages and they describe different commands with different documentation. So you can either do this, or it's much faster, you just put here in this form the command. For example, ls, and here it's gonna do a Google search that filters only the results from the website, men7.org. So here you get the first result, ls, and then you can get essentially the same thing you get from the man command locally, but this time it's through the web, so you don't need to install the man command. And so this covers this first introductory. I wanted to mention it because in the previous video I did not introduce the man pages, but they are really fundamental part to understand Linux. And when you're doing a box, for example in OSCP, and you find a command that you never used, the first step of course is to just read the main page, understand what the command does, and try to find maybe the specific option, the specific flag, or the specific arguments that allows you to do the privilege escalation. And so now we can actually get to the content of the video, which will be about file system permissions. So when we use ls with the option lha, so essentially with the option L, we're gonna get a lot of different information about our files. And specifically here, we have this first set of information which has to do with permissions. So technically what happens is that we have this set of information that has to do with permissions, and also this other one and this other one. So we have three things which have to do with permissions. And how we read them is that this is the set of permissions associated to the resource. So the resource most likely is either a file or a directory. This is not everything in Linux. You also have device drivers and special kinds of files, but you can imagine that any sort of resource is either a file or a directory, where a directory is a sort of special type of file that contains other files. So that's the general idea. So like in the first section here, you have the set of permissions associated with that resource. Then here you have the so-called owner of that resource, which is the user in the operating system that owns that resource. And then you have the group owner of that resource. So this is like the group owner, which is the same thing as the owner, but this time it's not a user of the operating system, but rather it is a group of the operating system. Because in Linux we have the concept of users and the concept of groups, and groups are essentially containers of users, so a group is made up of different users, and this means that a given resource can be owned by one user and by one group. So for example, consider this line, this exec.sh line. So here we have typically the sh extension is used to contain commands that will then go to a shell. So in the previous episode we discussed the role of the shell, and we said that the shell is a so-called interpreter of commands. So like we give to the interpreter commands encoded through text. The interpreter reads the commands, understands them, and executes them on the operating system. And these commands can do anything. They can modify the file system, they can modify the processes, they can start a new process, they can create a new file, they can check network interfaces, they can create a new network interfaces, so that the commands essentially have full control over the operating system resources, and they can just use them and manage them. So this is like a typical extension. Now, in the case of this exec.sh file, essentially what we have is that the owner of the file is the Leo user, which is my user. The group owner of the file is the users group. So this file is owned by the users group. And then we have this set of permission. We have dash rwx r-x r-x. So this is like the idea essentially. Now for each file we have the following information regarding permissions. So we have the file permissions, we have the user that owns the file, and we have the group that owns the file. So in this case, for example, we have this, which is found essentially here in this exec.sh. Now, as you can see, within each string of the form of this particular form, we find 11 letters. So there are always 11 letters. Actually, I think they are 10. So let's say they are 3, 6, 9, 10. So there are 10. So there are 10 different letters. And now the objective when understanding Linux file system permissions is to understand the meaning of each letter. Like, what does it mean when here there is an X? And notice that down here there is not. So down here there is a dash, but up here there is an X. What does it mean when there is this difference in the file system permission strings? So the idea is that permissions are encoded in this single string, and then we have a user and a group owner. So that's the idea. Now we find 10 letters, which can be either set or not set. So that's the idea. The first thing to understand is that each permission can either be set or not set. And when it is not set, so when it is not defined, there is a dash. So the dash stands for like the bit 0, stands for like we don't need that permission is not activated on that particular resource. So if you see something with all of dashes, it means that no permission is activated. For example, in this case, we have a bunch of different permissions that are not activated. In the uppercase, it's less. So that's the idea. So the first letter, so once we said that the dash is for not setting the permission essentially, then the first letter specifies the type of the file. So for example, when we have regular files, we just have a dash as the first letter. Instead, when we have directories, we're gonna have a D. When we have links, which are special files in Linux which point to other files, so it's sort of like I have a file here, but this file 1 actually points to another file, a file 2. Now this is called a symlink. This is called a symlink. And so in this case, for this file, the first letter would be the L letter because it is a symlink. So for example, let's consider the assets that form this lecture, like the notes and stuff like that of this lecture. So I do ls in the current working directory, which is this one. So it's like home Leo project foundation, then we have the YouTube, then we have Linux Privesk, we have 02 and so on and so forth. So this is the current directory. Inside this directory, I just have a single nodes.org file, and I can check the permissions of this file with the option ls lh. So with -l, essentially I get this listing, and with the h, I transform the number of bytes into a more readable format. So it says that I have 11 kilobytes of information. Now, with respect to the permissions, we know that this file is owned by Leo, by the user Leo, and belongs to the group users. So this is the first two pieces of information. Then we find this string of specific permission, and it says that the first one is a dash, which means that this is a regular file. Now, if you go back one directory with cd ... so we go back one directory. Now, if you do the same ls-lh command, we have three different directories this time. We have content, we have thumbnail, and we have video. And they all start with the D letter because they are all different directories. So content, thumbnail, and video. So that's the idea. If you see D here for the first thing, it's a directory. Otherwise, it's a regular file. And of course, the idea is that we can go inside a directory while we cannot go inside a file. We can just read the contents of the file. We cannot traverse it with the normal file system operation. So that's the first letter. It specifies the type of the file. Then what we find is we find three groups of 3 letters each, which means that, for example, this thing actually, how do you expand it? You expand it as follows. You have the first letter which specifies the type of the file, then you have a block of 3, another block of 3, and another block of 3. And notice that they kind of repeat themselves because they're like R, the first one is always R, the second one is always W, and the third one is almost always X. And this time at the end is T, we will talk about that later, but essentially look down, for example, so we expand this down, so we have D, which is like the type of the file, then the first set of permission, the second set of permission, and the third set of permission. So they expand into 3 groups of 3 letters each. Now, the first group specifies the permissions for the user who is also the owner of the file, which means that out of all these three different groups, essentially each group specifies a set of permissions. However, the difference between one group and another group is that, for example, the first group is specifying the permission of the file with respect to the owner of the file. It means that the owner of the file has this set of permission. However, if I am not the owner of the file, I do not have exactly this set of permission. So that's the idea. The second group specifies the permissions for the users that belong to the same group as the group that owns the file. And the third set of permission is for every other user. So it's like the first group specifies the permissions for the user who is the owner of the file. The second group specifies the permissions for the user who belongs to the group that owns the file. Finally, the third group specifies the permissions for all other users. So here it's users. That is, for users who do not belong in the group that owns the file and are not the owner of the file themselves. So the idea is that to read this kind of permission, we have to say, for the owner, we have to consider the first set, the first group. For the group, we have to consider the second group of permissions. It means that if our user belongs to the group users, then we have to consider this set of permissions. Finally, if we have a user who is not the owner and also does not belong to the group that owns the file, then we consider this other third set of permissions. If we imagine software like sets, the idea is that the most close set is just the user who owns the file. So the first permissions are the most like the one that only apply to the user that owns the file. The second is a little bit more big in terms of applicability because it's for every user that is on the same group of the group that owns the file, while the third one is for everyone else. So no matter who you are, the third group will always apply to you. So that's the way to read it. So now each group works in the same way. And the idea is that we have three different permissions. We have read permission, we have write permission, and we have execute permission. And they are signified, they are represented with three letters. R for read, W for write, and X for execute. Now there are minor variants in this, so like sometimes, especially with the execute bit, sometimes it's not written as X, sometimes it's written as S, other time it's written as T, so the execute bit is not always straightforward. Sometimes it can be different from X, but when it comes to the read and write, they are always read and write. So that's pretty simple to remember once you understand it. So for example, in this case, we have this exec.sh, but here in the owner set of permission in the first three, the execute bit is not X, but rather is S. This is because there is this mechanism called the SUID bit, which we'll discuss later on, which modifies how the program behaves with respect to permissions, but it's a special case. So here also in the group there is S. So for now, just consider that every group of permission has read, write, execute. So going back, what does it mean? It means that, for example, consider like we have this entry. So I'm gonna open a new buffer here. I'm gonna put it in org mode. I'm gonna go here and I'm gonna go, okay, suppose that we have this entry, example entry. So we have the file name, which is exec. So like we know that the user who owns exec is Leo. The group who owns exec.sh is users. Here Leo is lowercase. Then we have essentially for the Leo user the following permissions apply. So what do we have? We have read, write, execute, right? So we have read is set, write is set, execute is set. It means that the Leo user can read this file, can write to this file, and can execute this file. So this is really important. Then for the group users, the following permission apply. So what do we have here? We have like, can we read the file for the group? Yes, because notice that the second section of permissions, we have read and we have execute. We do not have write. It means that the group can only read and execute it, but it cannot write to it. Which means that, for example, if we are a user who is not Leo, let's say like another user, like the user X, so we are not Leo, but we belong to the users group, it means that for our user, the permissions that apply to this file are the second group, this r-x, which means we can read it, so we can read its contents, we can execute it, but we cannot write to it, which means that we cannot modify it. We just can read it and execute it. So this is for the group users, and then for every other users, the following permission apply. So once again, if we are any other users, now we have to consider the third set of permissions, which is once again just read and execute. So that's how you should read this kind of permissions in Linux. This is like essentially the core idea. You go to the name of the file, you check who is the owner and who is the group that owns the file. Then you go look into the permission and you say, okay, what kind of file is this? This is, for example, a regular file. And then finally you take out the 3 sets of 3 permission each and you say, okay, the owner can read, write and execute it. The group can just read and execute it. Everyone else can just read and execute it. So this is what typically happens with critical scripts, which you want your systems to execute. You want them to read the contents. However, you do not want them to modify the script because maybe it's like critical and you just don't want to do that, but you want to allow them to execute it if it's needed, but you don't want them to modify it. So like this is how you read this kind of permissions. Now that we have covered the basic concepts, we can do some practice into reading file system permissions. So to read the permissions, we can use the ls command. So we can do ls with -lha. So A is to show the hidden files. H is to make sure that the file contents are printed in a readable way. So with, for example, kilobytes, megabytes, gigabytes, and so on and so forth. L is to show all the information regarding permissions. So we can analyze such output line by line as follows. The first line is referring to the current directory. So this is the dot. Dot means current directory. It is saying that it is a directory because the first letter is D. It is owned by Leo, which means that the first group of permissions apply to the user Leo, and particularly they're telling us that Leo can read R, because here there's an R, can write to it and can execute to it. So he has full permissions over the file. He can do anything he wants over this current directory because it is owned by Leo. Now, this directory belongs to the group users, so the users instead can read and execute the directory but cannot write the directory, which means that they cannot write new files into the directory. So that's the idea, while every other user can read and execute but cannot write. So it means that this directory is owned by Leo and only Leo can write new files, while everyone else can just read the contents of the file already existing in general. So that's the idea. Now the second line is saying that it applies to the previous directory, not the current, but the previous. So remember, in the previous video we introduced the idea that the file system is a tree of resources starting from the root, which is represented with the slash, and then we have different directories or files. Then if we have, for example, a file.txt, that's it, this is like the last node of the tree, while if we have a directory, we have other nodes, because we go down, we go deeper into the structure of the file system. So for example, in home, we have the directory for Leo, and then we have other files here. So this is the current directory in this case, it will be this node, so it will be this node, while the previous directory, it will be the home folder. So this is why the previous directory is actually owned by root, because Leo just has access to his own home directory, not to the home directory itself. The home directory itself is owned by root, which is the administrator account in Linux systems. And it is saying essentially that the user root can read, write and execute on this directory, and essentially also all other users. Why? Because here we have all permissions for all users, so they can both read, write, execute, and read, write, execute. So everything can write into the home directory. So that's the idea. Then, for example, just jump into the last line. The last line is referring to the resource test.txt. It is saying that it is a regular file. Notice here, the dash is a regular file. It is owned by Leo, it is owned by the group users, and Leo can read and write its contents, while everyone else, so users belonging to the users group, or any other user in general, they can just read their contents. Like they can just read the contents of the test.txt file, but they cannot modify it. So this is sort of like saying Leo, the owner, can modify it, everyone else can just read it. And essentially it's the same for the exec.sh. However, for the exec, the difference is that the users that are not owner of the file can also execute the file. It doesn't happen with test.txt because test.txt is not really an executable. You just read it, you don't need to execute it, which means that you don't need this permission to execute it. While with exec.sh, given that it's like a shell script, is a command, it's like it encodes commands that are executed by the shell, you probably want to execute it, because the idea of a shell script at the end of the day is to execute it, is to do some task automatically. So essentially, that's how we read this kind of contents. You just have to do practice day by day to understand the permissions. If you check a problem with permissions, it probably means either you do not have that specific permission, or maybe you are not the owner of the file. So for example, if you're trying to update a file, you always need to understand, wait, do I have the write permission? Do I have the W permission? And if you see something like this, something like test.txt, you try to write to it, but you're not the owner, then you will encounter a permission problem, because only the owner can write to the file. So essentially that's the idea. Now there are some special cases that you need to consider. Here I just mentioned 2. You have other special cases, but the point of this video is to introduce the file system permissions, not to expand all of its details, because once again, the idea is once you understand the basics, the fundamentals, then you can look into the documentation, you can look into the main pages to understand all the subsequent details. So for example, here I mentioned 2 special cases. Sometimes it can happen that for the last position of the value, you will see t instead of x. So typically the last one is this xxxx, but sometimes you see t. This is called the sticky bit, and essentially it implies that the users in the group who technically have the permission to delete a file cannot do it as long as the sticky bit is set. So it's sort of like it modifies the way that the permission works. So consider this. You have a t, you have a sticky bit here, t. So it means that it applies to the previous directory. So that's the idea of the sticky bit. You don't need to understand it completely. It's just saying that there are special cases in which you will not see x, but you will see a t. Another special case, which is actually much more important than the sticky bit, is this. Sometimes instead of x, you will see the value of s. Now this instead has to do with the SUID and GUID permissions, which will be discussed later in this section, SUID and GUID. So this is it for when it comes to reading file system permission. Now we can talk about, okay, how can we set our specific permissions? How we can update the permissions of a file? So here the idea is to use the chmod command, which is for change mod, sort of like change permission, chmod. So you can search the main pages for chmod. Here I will showcase simple examples. So let's assume that you start with the following file. So you have an exec.sh, everyone can read it, but only the user can write it. So this is a regular file. The owner of the file can both read and write it, he cannot execute it, and everyone else can just read it. So the group users can just read it, and every other user can just read it. Now, suppose that we want to add the execute permission for all types of users. So for all groups of permissions, which means for the owner, for the group, and for everyone else. How would we do that? Well, we do chmod, then we do plus x because we are adding this permission, and then we put in the name of the file. So in this case, it should actually be exec.sh. So once we do that, and after that we do an ls, notice what happens. Here we modify the permissions as follows. So before we just had read write, now we have read, write, and execute. Before we just read, now we have read and execute. Once again, before we just read, now we have read and execute. So to add a permission, we do plus x with the name of the file. So for example, let's say I create a new file, test.sh, I do ls, and here test.sh does not have the execute bit. To add it, I do chmod plus x test.sh, I do ls again, and notice that now it has the execute bit, And also ls by default actually colors this in green. This is because, this is like a little note for those curious, why does it color in green? Because actually ls by default is called with a special argument, because there is a so-called alias in ls, and when we actually execute ls, we are executing ls color equal auto. So we are actually doing this, and when we do this, it uses like specific environmental variables which govern how different files should be colored in the shell. So if you remove this, I think it's like never. If you remove this, if you say color never, notice that we do not get this color grading. We do not get colors anymore. However, if you do color auto, we get back again. And we can also do just with ls, so ls like this, because there is a concept in bash called the alias. We can do alias ls, which means every time you execute ls, what you're actually executing is ls dash dash equal color auto, dash dash color equal auto. So that's the idea essentially. So continuing, that's how we can set the permissions. So this is like adding a permission, right? Now, how can we remove read and execute permissions for other users? So this is the third group. The third group, which means users that are not the owner and do not belong to the group that owns the file. So in this case, we have to do a minus. We say minus xr to say, I want to remove the execute and the read permission, but before this minus, we have to put O, which stands for others. And this others here, it means not the owner of the file and not the group that owns the file. So like this chmod command, the structure of this chmod command is, here we specify the sort of like group we are targeting, and if we do not specify the group, like in this case, it will apply to all three groups. And then after we specify the groups, we have to say plus to add a permission, minus to remove a permission, and then we write all the letters that represents those permissions. So this is like add to all group the execute bit. This is like remove from the others group the execute and read bit. And for example, here we say add write permission for group that owns the file. Why? Because we use the G keyword. So like while O was for others, so O others, G is for group, which is the second section of permissions. Because remember, the first section is for the user that owns the file, and this in chmod is represented by the U. The second is for the group, and the third is for the others. So that's the idea, that's the structure of Linux permissions essentially. Now, suppose you have a directory and you want to make a change across all the files in the directory, right? Because a directory essentially is a container of different files and directories, so it has a recursive structure. Now suppose you want to make a change into all the subtree, into all the structure that is represented by the directory starting from the directory, then you can use the recursive option -r, capital R. So in this case it would be, okay, you're gonna remove all permissions from the others section, all read, write, and execute across all the directory, because it is recursive. So essentially this is the idea. So for example, so let's do other examples here. So we have this file, so we have content, we have this test.sh. So let's say that I want to remove those permissions from the others group. So I say chmod. I specify the group I'm interested in, which is the other, which is the third section of permission, and then say, look, remove, read, and execute. Then I do ls again, and notice that it's gone. The read and execute is gone. Say now that I want to add all permissions for the group, and I want to remove all permission for the user. So I can say chmod user minus rwx group plus rwx test.sh. So I do this. So I think I have to do one at a time actually. So first I do the user, and then I do the group, then I do the group, and then I do ls again, and notice now the owner of the file cannot actually do anything on the file. The users belonging to the group users, so the group of the file, can read, write, and execute, and the others can do nothing, because first I remove all the permissions from the owner of the file, which is represented with the keyword U, and then I add all permission to the group that owns the file, which is represented by the keyword G. So the chmod is really simple. You just have to like select the group you want to operate on, which can be either U for the owner, G for the group, or O for the others. Then you put plus or minus, plus if we want to add permissions, minus if we want to remove permissions, and then you put the series of symbols which represent those permissions taken from RWX. R for read, W for write, X for execute. So that's the general idea. Now continuing, there's actually another way of dealing with permissions. Sometimes we can use numbers essentially. So we have Y, because since permissions are like bit mask, are like sequences of bits, so we have that the no permission belongs to the sequence 000. The execute permission like this belongs to the sequence 001. The write like this belongs to the sequence 010. So we have a mapping between the set of permissions we want and sequences of bits, and then we can map those sequences of bits with numbers. So that's the idea. So like, this is essentially the idea, is that given that with 3 bits we can represent the numbers from 0 to 7, this means that each number can represent a specific set of permissions. So it's like, essentially said, instead of using the identifiers UGOA with RWX, it is also possible to set permissions using a sequence of 3 numbers. This is because read and write and execute permissions can be represented using 3 bits, and we can also represent the numbers from 0 to 7. Specifically, we have the following association between bits, permissions, and numbers. So this table is really useful to keep in mind. Full permission 111, which is 7. Read write dash 110, which is 6, and so on and so forth for all the 8 examples. So for example, a 5 is actually representing read and execute. This means, for example, that 5 represents the read and execute permission bits, while the 7 represents the entire read, write, and execute bits. Remember that we have 3 groups of users. This means that to fully specify the basic permission for a file, we will need 3 numbers, each going from 0 to 7. So for example, what does it mean? So let's go back to our Scratch buffer. We have another example here. It's like, so we have another example here. So we have example 1, and then we have example 2. So we have example 1 and example 2. Now, in terms of example 2, we start with this, let's start here. We start with this. So what chmod 764, what does it do? Well, we have to use our table like this. So our, essentially this translation table, which is really useful. So we keep this in mind. And then we say, so like, let's just transport it like this. Okay, and then we say essentially, okay, so 7 stands for, so like 7 stands for this, 6 stands for this, and 4 stands for read dash dash dash, which means essentially that this is gonna give the permission to the file like, okay, the owner is gonna have read, write, execute. The group is gonna have just read and write, not execute, and everyone else is just gonna have read. And so this means that this is the permission mask that we want to see on the file after executing this command. So what do we get in our notes? We can say, look at this, we get read, write, execute. So read, write, execute, then we have read, write, and then we have just read. So for example, let's do in practice in a real working shell. So we have this test sh, so right, we have this test sh. So we do chmod like this with testo, and then notice here what happens. We have exactly this mask. We have read, write, execute for the owner, read, write, execute for the owner. We also find it here. Then we have read, write for the group, read, write for the group, and we have write for everyone else. And we obtain this set of permission with the numbers 764. Why is that? Because each number in this is representing 3 bits. So 3 bits, because we have numbers from 0 to 7, and each 3 bits is representing a set of permission between R, read, write, and execute. So with this table, just keep this table in mind. You're gonna find it in the notes for this episode. Just keep this table in mind, and by going from the number to the permissions, you'll be able to understand the effect of that particular chmod command. So for example, another thing is that if we want to set read, write for the user, read for group, and nothing for others, so we can say read, write, because it's sort of like we have 1, 1, 0 for read, write. So this is like, this is 2, and this is 4. So this 4 plus 2, that's 6, no? This is like the translation between binary and decimal. Then we have, so like this is for the owner. For the group, we just want to read, right? So we have 1, 0, 0. So this is like 4. So this is like 4. and nothing for the others. So we want 0, 0, 0, and this is of course is 0, which we find it here at 0. So with this chmod, we get read write for owner, read for group, and nothing for others. And so this covers essentially the basic working of the Linux file system permissions. To finish off the video, we will talk about two specific mechanisms, which are the sudo and which are the SUID and GUID bit permissions and the sudo system. Now, certain executable files can have special permissions called SUID and GUID. So these are like special bits in the permission, which are called SUID and GUID. Now, SUID stands for set user ID. Now, the idea is that binaries that have this bit allow the binary during its execution to change user permission. So for binaries that have this setUID bit, this set user ID, the idea is that typically they run with one set of permission, but they can change that set during its execution. So specifically, these kind of programs can be executed by anyone. And if they are executed by anyone, first they will start their execution with a set of privileges associated to the user that executes them. So for example, if I am Leo and I execute a program with this kind of thing, initially it will execute with my permissions. However, during its execution, they have the choice. They can change their permission and take the permissions of the owner of that binary. It means, for example, that if I am the user Leo and I execute a program, and this program is actually owned by root, so it's like owned by root, and this program has the SUID bit on, it can change its privileges during its execution from Leo to actually root privileges. So this is really important, and one might wonder, why do we need this mechanism? And this mechanism is useful when you want a program that can be used by anyone, but needs special permissions in certain cases. So for example, consider the program used to change the password, which is this, passwd. So you can use this command to change your user password. What does it mean? Let's just reason about it. It means that everyone should be able to use it, everyone should be able to execute it, because every user at any point should be able to change their password. But since we are changing a password, we need to save the new password, and specifically we need to save the hash of the new password into a privilege file in the system, which will then be used for later authentication. So the idea is that this program has to write to a specific file which requires high privileges, which requires root access. So the idea is that anyone should be able to use it, should be able to run it, but then at some point this program has to write into root-owned files that only root can actually write to. So at some point in its execution, this program will need to elevate its privileges, and it can do so with this particular bit, the SUID bit. So notice that if you do this in your system, this is the typical location of the passwd command, and you do ls-lh, here, instead of execute bit, you will see the S, which stands for SUID, and it is owned by root. So in the shell, typically, this is represented in red, because it's kind of a dangerous thing. So notice this. It's in red here, because this is like kind of a dangerous thing. And it is kind of a dangerous thing because during its execution, at some point, it will become root. So it's something to be careful about. So the executable bit flag is not X, but rather S. This is because the program has the set SUID bit set. This means that during its execution, at specific times, the program will change its roles in order to become root. This change of permissions is done by using the function setUID offered by the standard C library. It is necessary since the shadow file is owned by root and only root can edit it. So this is the actual source code. Here I put a link. Here you can just click on the link. It's like the source code of the shadow implementation of the passwd implementation. And in this source code, at some point, you will find this line. So it's the setUID 0. And then it says if setUID 0 is not equal to 0, we have an error. So we cannot change ID to root. After we do that, we say update shadow, or else update no shadow. So essentially the idea is that we update the shadow file. Now the shadow file is the file that contains all the hashes of the password of your users. I showcased it in the previous video. It's like if you go into user management, here there is an example of a shadow file taken from a Docker container. So in this file, you see all the users, and then here, for example, for the SSH user, there is the hash of the user. So when we call the passwd command, the idea is that we need to update this file. We need to update this etc shadow file. But of course, the problem is that this file is owned by root, and its permissions are like this. Only root can read and write to it, which means that to make sure that everyone can use it, that everyone can update their password, but they also update this specific sensitive file, the idea is that, okay, the binary has the SUID bit on, and in a specific moment during its execution, thanks to the SUID function, it will elevate its privileges, it will become root for a moment, for just a brief moment in time, it will update the shadow file, and then it will go back on to execute as a normal user. We want to limit the window of execution in which we are root, so this is like the root execution, and this is like the entire execution. We want to make this window as small as possible, because the larger it is, and the more vulnerable we are to specific attacks, to privilege escalation attacks. Because if we have a program running as root that we, the user, can control, it could be dangerous. So the idea is, I'm just gonna elevate my privileges for a little moment just to update the shadow file, and then I'll go back to run as a normal user. So that if I get compromised during my entire execution, right, the moment where a compromise could actually become dangerous is very limited. It's just the tiny window where I become root, and all the other times I'm the user Leo, and after that I'm still the user Leo. If I'm compromised in these two windows, nothing happens, because you will get execution as Leo, which you already had previously, so there's nothing new. However, if I get compromised during this window, then you get execution as root, which of course can lead to privilege escalation. So this is why this SUID bit this mechanism has to sort of like being handled carefully. You have to be careful when you put a SUID bit on something. To actually set a SUID bit, you can just use the S flag. So like the S meaning is like execute, but with the SUID. So you can say exec with user plus S, and notice here, so like let's say that we do this. So we have this test sh, right? So we have this test sh, then we say chmod u plus s test sh, and then here we have this thing, and this thing is only for the user. So this is the idea, only for the user. So here actually should be an X. The same idea, however, applies also to the group permissions, but this time it is called GUID, not SUID. It's called with a G because it's group OID. And we can also use chmod. It's just that instead of the U, you can put the G, so G plus S, and you're gonna have an execute bit. Instead of X is S because you have used the SUID mechanism, but however it's called GUID because it is applied to groups. It is the same thing. It means that during its execution, at some moment in time, the binary can have the privileges of the group that owns the file. It's the same idea. It just applies to the concept of groups and not single users. If you want to set the S bit for both user and group, you can just do plus S. So the idea is that you do. So let's remove it from the user. Now we don't have it for the user. If we do a simple plus S like this, we're gonna set it for the user and for the groups. So notice this S and S, capital S here. So that's the idea. So actually in this case, it is a capital S because previously the group could not execute the file. So to actually make a lowercase s, we have to do G plus 6. I think with G plus 6 it should be good. Yes, now it's a lowercase s. So once again, it was a capital S because initially the group could not execute the file. Then we did give the GUID permission, but it still could not execute the file. So after we gave also the execution file, it became a lowercase s once again. So that's the idea. Finally, we have to talk about sudo. So an important subsystem that relates to permissions in Linux is the sudo functionality. Now sudo stands for super user do, and it is a utility in Linux that allows a user to change user for the execution of specific commands. So it's sort of like saying, okay, you are the user Leo, but you can execute a specific commands as if you were the user root or the user another user. So you sort of like you execute a command with a different user. And this is especially useful when you want to execute command as root, so that instead of being root all the time, you are your normal account, Leo, but then if you want to execute a root command, you say sudo and then, for example, you install a package. So for example, in the previous video, I showcased that for package management, you always had to use the sudo command, because packages, like these kind of managers like apt or apt-get, they typically write into sensitive places in your file system, so they need higher privileges. So to actually get them, you can use the sudo to say, okay, this command you execute as root, and once you're done with the execution, you go back to the previous user, which is like Leo or whatever users you were. So like once it is installed, we can check the way we can use it with the sudo-l. So for example, here I have a bunch of sudo-l commands, outputs from like ActBox machine and stuff like that. So the idea is that these commands tells us how we can use it. So for example, in this case, it was like a canopy machine. It says, look, you can broot to execute this command. So user bin pip install and then anything here. So the idea is that you can install with pip as root anything you want. So of course, this kind of configuration is vulnerable to privilege escalation, because by inserting a specific Linux package here, you can get actually root execution, because you are able to execute this command as root, but this command can be anything, because this asterisk, you can place any sort of Python package, and if you craft a malicious Python package, you are done for, essentially. You become root. Then this is like another, it says all, no password, user bin Python, like another asterisk, home Richard test. Essentially it means you can execute this command using any user you want without password. So we can be root, we can execute Python like 3, we can execute this script, and once again we have privilege escalation, assuming we can write into here. If we can write into here, we have privilege escalation. Another entry is like, okay, as root you can execute this user bin tryharder. So depending on how this binary is implemented, we can maybe find some kind of bug in the logic and we can exploit it to become root, because once we execute this tryharder, we are executing it as root. So this is essentially the idea. Another thing is that no password all, so like with every user, you don't need to put a password, you can execute the docker network inspect command and docker network ls commands. Another is that you can execute, this is like even more dangerous, because it means you can execute using the script manager user and group, you can execute all commands without a password. And actually I showcase how to do this in the bash machine. So in my ActBox, so like in my ActBox bashed, here I also have the report, essentially report content PDF. So you can watch the video, you can also watch the video where I read this report. But at the end, so we have here, so the first pivoting from www-data to script manager is like, once inside as www-data, we can check the sudoers and we have this configuration. So like the idea is that we can just do this. This of course is like a critical vulnerability, because with this payload, so we say sudo-u script manager, it means execute the following command as a script manager. You do python 3-c, so like you create a bash with a tty using Python, you spawn that, and then you are script manager. So this allows you to become script manager to the pivoting to script manager, and then you can spawn a shell and stuff like that, because the sudo configuration was vulnerable. So this is all to say that the sudo program allows you to execute commands as other users. It can be a normal user of the system, like script manager, or it can also be a root, like in this case all, it means all users of the system, including the administrator account, which is root. And here it says, if you have to put a password, so if you say no password, it means that you do not need to authenticate to that user. And here you have the specific commands that you can use with that user. So the sudo subsystem is extremely useful to analyze for privilege escalation. I will do a specific video on it, on how to abuse it, because for example here I showed a lot of vulnerable configuration of sudoers. So these are like configured in the file /etc/sudoers. The idea is that here you configure how you can interface with the sudo command, and then you can just check your configuration with sudo-l here. And once you have your configuration, you can check if it's vulnerable, if you can exploit it, if you can abuse it. And typically in, for example, OSCP-like scenarios, in CTFs, many times the sudo-shell is vulnerable to misconfiguration, and you can actually exploit it to do privilege escalation. So this is like a very common pathway to privilege escalation. So this covers everything for this video. We talk about file system permission. We also talk about main pages, which are extremely useful resource. For example, you can do like man chmod. Here you have all the things about the chmod of the different things, all the different documentation. You can do man sudo. You have all the execute a command as another user. So this is like all the things regarding sudo, how to use it. There are a lot of things here, of course, a lot of considerations and stuff like that. Then we talk about the file system permission, how we can read them. So how we can make sense of this output, how we can update them, how we can write them with the chmod command. And okay, here I did not talk about it essentially, but so the chmod is to change the permission. If you want to change the owner of the file as last thing, what you do is to do chown. So you do chown and then you put the username. So for example, chown root test sh. Of course, to do this I need to be root, so I need to do sudo. So with the chown command, you actually can change the owner of the file. And I think that the chown command, if we do chown -- help, it should also be used to change the group, I think. Yeah, you can see this is like owner : group. So the idea is that, for example, if we say sudo chown root with the name of the file, we do this, and now we also change the group of the file. So we can add this because it's important in the updating file system permission. So here essentially it's like, okay, I would say that we can do this section here. To change the owner of the file, we can use the chown command. So the chown command, so it's like chown root test.sh. If you want to change the group, you can use the syntax with the colon here. So it's like chown user group test.sh, like for example, chown root : root, like root : root test.sh. And then if I do ls lh like this, I get back this, which is useful to showcase that we actually change the stuff. So you can also use the recursive -r flag to make it recursive. I mean, there's of course, as always, a lot of things to say, but the chown is extremely useful to just change the user. This is for the -recursive to operate on an entire substructure, subdirectory structure. And after that, after the chmod and chown, we are essentially set. We talk about the SUID and GUID and the sudo. For these last two topics, I will make specific videos on privilege escalation, abusing the SUID bit and abusing the sudo configuration. So that's it for this video, and to the next video.